the truth did was it made the endothelial lining of the pores, fenestra, it made them negatively charged. And then something like really small, like angiotensin, also negatively charged. Because now if something negatively charged urged the negatively charged fenestra to get out, it would be moved out. So the ultrafiltrate has no protein in it. There's one more thing that helps prevent proteins from escaping, and that is these cells here, podocytes. See how they have extensions that are interdigitating with other extensions? Those will also prevent other proteins that are inside of the lumen from just being able to float out. I've already talked to you about the word ultrafiltrate. It is the stuff that has been filtered over the glomerulus that is inside the nephron tubules. Glomerular filtration rate, that is the volume of filtrate that's produced by both kidneys 1 minute. It is a little bit higher in males than females. Males are about 125 mLs per minute, and females are about 115 mLs per minute. If you chug the numbers, what that means is that about 5.5 liters of blood are filtered over the glomeruli in about 40 minutes. Remember about how much blood humans typically have? It's about 5.5 liters. 5 to 5.5 liters. What that means then is the total volume of blood in the body is filtered by the kidneys in about 40 minutes. That is a lot of work being done. Plug and chug those numbers, that means it's about 180 liters per day. My mind's eye does not see liters very well, but I see gallons really well. That is 45 gallons of blood are being filtered by the kidneys in about 24 hours. That's amazing. You know that we only urinate out maybe 1 to 2 liters per day. That means that 99% or so what gets filtered has to be reabsorbed. I hope you guys are getting a good idea of how much work is being done by the kidneys in a day. It's amazing. That reabsorption is being controlled extrinsically and intrinsically. Vasoconstriction or dilation of the afferent arterioles really determines the blood flow to the glomerulus, and then therefore has a lot of control over how much gets filtered. I am going to ask you one essay question on the reabsorption of salt and water. This is the last one of the semester, I'm pretty sure. Awesome. Okay, so it doesn't start on this slide. I want to wake you up in case you're not listening. Okay, so a well-hydrated person, and I've been telling you all semester that most humans stay in a state of dehydration. It's not extreme dehydration, it's slight dehydration. That just comes from the nature of us being made mostly of water, living in an environment that is not mostly water. Okay? A well-hydrated person can make up to 23 liters per day of urine. I doubt most of us have done that. Okay? Severely dehydrated person, somebody who's going to die of dehydration, they are still going to urinate out about 400 mLs per day. That is because that is the minimum amount of water that has to be put out to get rid of the metabolic waste. So that 400 mLs per day is called obligatory water loss. Okay. So you guys remember that we never actively transport water. That creates a problem with reabsorption of water early on in the nephron. Let's take a look at the next slide. So this first panel here, what is filtered? The filtrate is actually isoosmotic to the tissue fluid and to the blood, about 300 milliosmoles across this whole thing right here. So then how will we get the water reabsorbed? And the truth is about 65% of the water, salt and water, is reabsorbed early in the nephron, right at the proximal convoluted tubule. How is that going to happen? This is where the answer to my essay question really starts. Okay, what's going to happen is in the proximal convoluted tubule, sodium ions are going to be actively transported out of the nephron tubule and into the interstitial space. So we're going to take a bunch of positive charges, move them out of the nephron into interstitial space. That is going to create a electrical gradient, create an electrical gradient for chloride. Chloride is going to want to follow the sodium. So it will just follow passively. And then water is going to follow by osmosis. Okay? About 65% of the water, chloride, and sodium is going to be reabsorbed at the proximal convoluted tubule in the way that I just described. And my answer key does describe the fact that sodium has to be actively transported out the filtrate. Chloride will follow its electrical gradient passively, and then water will follow those two by osmosis. 65% is removed at the proximal convoluted tubule. Then at the descending limb of the loop of Henle, another 20% is going to be reabsorbed. So by the time we get to the base of the loop of Henle, 85% of the water and salt are already reabsorbed. That is going to be consistent and independent of hydration levels. It doesn't matter how hydrated you are, at 85% is going to be reabsorbed automatically. The other 15%, that is going to be reabsorbed variably, and that depends on the needs of the body, how hydrated we are or not. So 15% doesn't sound like a lot in the world we live in. For example, if you've got $100 in one hand and $85 in another hand, well, we'd like to have 100 in both, but both hands are happy. That's okay. But when you're talking about 15% of glomerular filtration rate, which is, again, 180 liters per day, if I can chug those numbers, that's 27 liters of fluid. Can you afford to lose 27 liters of blood per day? No, we only have about 5 to 5.5 liters. So when we're talking about glomerular filtration rate, 15% is a lot. Okay? So the way that 15% is going to be reabsorbed is by hormones that act on the collecting duct and on the distal convoluted tubule. Aldosterone is going to act on the distal convoluted tubule. So please add that in. Aldosterone acts at the distal convoluted tubule. An antidiuretic hormone acts at the collecting duct. Antidiuretic hormone acts at the collecting duct. And that ends. You notice that this line right here, underneath the underlined line, this one right here, I didn't say it in my answer. You really don't need it. Okay? Okay. So something interesting happens as we move down loop of Henle, down the descending limb, the loop of Henle, and then back up ascending limb of the loop of Henle from the proximal convoluted tubule. The ultrafiltrate, it's really, really concentrated. Look at this bottom picture here. Started off again at 300 milliosmoles as we went into the descending limb of the loop of Henle. As you go down, 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 look at what's happened to the concentration. It's more and more concentrated. From 300 to 600 to 800 to 1,000 to 1,200 until we get to the base of the limb of the loop of Henle. We're at 1,400 milliosmoles. And look what happens as we go up ascending limb. Go 1,200, 1,000, 800, 600, 400, 200. Now we're below what's in the blood. 100. Okay? This is brilliant for a number of reasons. It has a name. It's called the counter current multiplier. And I do have it typed up for you in the next slide, so don't worry about it. Results from a positive feedback loop between the descending limb of the loop of Henle and the ascending limb of the loop of Henle. This is what happens. The descending limb of the loop of Henle is permeable to water, not salt. And the ascending limb of the loop of Henle is permeable to salt, not water. So this is what happens. As the ultrafiltrate moves down the descending limb, water is extruded out. More water comes out, it's coming out on both sides. If I had made this diagram, I would have shown water on both sides, just like they showed chloride, sodium chloride on both sides. I don't know. They don't know the physiology, so they didn't know it wouldn't make sense. Water's coming out here, water's coming out here, water's coming out here. Then as we move up, remember that descending limb is not permeable to water, it is permeable to salt. So since we put a bunch of water in here, that is going to drive the salt out, 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 out. And again, because you put a bunch of salt out here, water is going to be driven out, 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 out. And I hope that makes sense to you. Okay, so there's a positive feedback loop. The more water the descending limb, the loop of Henle puts out, the more salt ascending limb puts out. The more salt the ascending limb puts out, more water descending limb. And this way then, as you move down, get more and more and more concentrated. And as you move up, it gets less and less and less concentrated. Okay? It's actually brilliant to make what goes into the collecting duct less concentrated than the interstitial fluid. We'll see that in just a moment. Okay, so this is talking to you about what I just said. I would like you to please cross out the entire bottom part of this slide where it says active transport AT and the descending limb of the loop of Henle all the way down. Cross that whole thing out. Here is what I just told you in words about the countercurrent multiplier system. Okay. Collecting duct, I mentioned a moment ago that antidiuretic hormone acts at the collecting duct and is brilliant of nature to do. Let me remind you what antidiuretic hormone does with those aquaporins. Remember what insulin does for the GLUT transporters? Insulin causes the GLUT transporters to be taken to the membrane and inserted into the membrane so that glucose can be transported. Antidiuretic hormone does the exact same thing for aquaporins, those water channels. Okay? Here it is typed in for you. So let's focus on this bottom picture here and collecting duct. Remember that by the time the ultrafiltrate is moving towards the collecting duct, it's now 100 whereas what's in the tissue fluid is higher than that. So there's more water in the collecting duct than outside. There's a higher concentration of water. So when antidiuretic hormone interacts with its receptors, it causes those aquaporins to be put into the membrane of these cells. And then will allow water to move by osmosis from an area where water is more highly concentrated into interstitial fluid, into the blood. Water's moving out. We're only showing it moving out on this side. It's moving out along the whole thing. Okay. I told you guys before that there are two types of diabetes. There is diabetes mellitus and diabetes insipidus. The mellitus one we've gone over pretty thoroughly. It has to do with sugar, hyperglycemia. Diabetes insipidus has to do with either a lack of antidiuretic hormone or a lack of antidiuretic hormone function. This is going to be a really bad situation because without antidiuretic hormone, literally we would be to death in a few minutes. It would be horrible. Okay. All right, renal clearance refers to the kidney's ability to remove substances out of blood and excrete them into urine. Okay. It occurs by two ways. One is filtration. The nephron filters something out of blood and puts it into the nephron. You guys know it's going to end up in the urine as long as it's not reabsorbed, right? The other way that it occurs is secretion. Remember we talked about the liver conjugating xenobiotics to anions, and those were transported through the kidney where we had those multi-specific organic anion transporters. Those transporters are sitting here in the proximal convoluted tubule, and molecules are being secreted in. The reason they're being secreted is because they cannot be filtered over the glomeruli. So nature made those multi-specific organic anion transporters, stuck them in the proximal convoluted tubule, and there you go. Those molecules will be secreted in, not going to be reabsorbed, so they're up in the urine. Now, reabsorption decreases renal clearance. Again, renal clearance is the ability of the kidneys to remove substance from the blood. So if the kidneys are filtering it and then it's being reabsorbed, it's going to go back into the blood. Okay, so reabsorption decreases renal clearance. All right. On the bottom half of this, we've already discussed. The very last one talks about the half-life of therapeutic drugs. Remember that half-life is the time that it takes for half of that substance to be removed. So having those organic anion, multi-specific organic anion transporters at the proximal convoluted tubule is going to help get rid of those drugs from the blood. I've never had an inulin test. I've never had my kidneys tested, but I'm sure some of you have or know somebody who has. Inulin is used clinically to assess kidney function. Inulin is a fructose polymer that does not occur in the body naturally. Inulin can be filtered. It cannot be reabsorbed or secreted. It can be filtered, it cannot be reabsorbed, and it cannot be secreted. So if they want to check how your kidneys are functioning, if they're filtering correctly or not, would give somebody this inulin polymer, because when they find it in the urine, they know the only way it got there was because the kidneys are doing their job. If they don't find it in the urine, then that means the kidneys are not filtering correctly. Okay. So we talked about in lab why it is that glucose is never found in urine under normal circumstances. Anyone remember why? It is because it is 100% reabsorbed. Glucose, unlike proteins and blood, is actually filtered. Same thing with amino acids. They're very small and they do get filtered, but under normal circumstances, they're 100% reabsorbed. Okay? The only way that you're going to have glucose or amino acids in urine is if their transporters saturated, or if the transport maximum is reached. Again, concentration of glucose or amino acids is so high in the blood that all the transporters are there, they're doing what they're supposed to do, they're working as fast as they can. We've hit their transport maximum, they can't work any faster. We have saturated transporters, then we would end up having glucose or amino acids in the urine. Okay? Under normal circumstances, they don't saturate. In glucosuria or glycosuria, I mentioned both of these to you in lab. That means that there's sugar in the urine. Okay? This normally does not occur until plasma glucose levels go above 200 milligrams per deciliter. Okay? That number, then, that 200 milligrams per deciliter would be called the renal plasma threshold. That is the minimum plasma concentration of a substance that's going to result in its excretion. Okay? Glucose is normally absent in urine because your blood glucose has to be higher than 200 milligrams per deciliter to reach the transport maximum 375 milligrams per minute. Okay? Usually after a meal, we go up to about 150 milligrams per deciliter. You guys know hyperglycemia is the hallmark of diabetes mellitus. Discussed that pretty thoroughly. Okay, I mentioned this on the first slide that the kidneys regulate the concentrations of sodium, potassium, hydrogen, bicarbonate, chloride, phosphate. They got a lot of rules. You know that sodium and potassium are important for the electrical activity that our cells do. Carbonate and hydrogen ions have a huge role in pH. Chloride and phosphate, you know that phosphate is used for bone deposition. Chloride is also important for the electrical signaling that our cells do. Okay, we're familiar with that. Here we go in the middle again with the renin, angiotensin, aldosterone system. I can ask questions off of this, but I'm not going to ask that essay in here again. You know that aldosterone secreted from the adrenal cortex in response to low blood pressure. Okay. Aldosterone goes again to the distal convoluted tubule and causes the reabsorption of sodium and water and the excretion of potassium. Okay. When aldosterone concentration is very high, all the remaining sodium is going to be completely reabsorbed. Okay. Here it is, typed out again. I feel like I beat you up with this in the last one, so I don't even want to go with it again, but I'll go over it just in case you want to hear it or it helps at all. I'll do it fast. Okay, so angiotensin is made by the liver and it just floats in the blood. When blood pressure falls, the kidneys sense this. There are actually stretch receptors. I didn't tell you this, but in case you want to know, there are stretch receptors in the efferent arteriole. And when blood pressure falls, the kidneys sense this. They then release an enzyme called renin into the blood. Renin cleaves angiotensin to angiotensin 1. Angiotensin 1 then goes to the lungs, where there is an enzyme called angiotensin converting enzyme, or ACE. Angiotensin converting enzyme cleaves the angiotensin 1 into angiotensin 2. Angiotensin 2 is active, does a number of things all aimed at increasing blood pressure. The one thing it does is it goes to the hypothalamus and it has the hypothalamus trigger thirst. So that will take in more water and that would increase our blood volume and increase our blood pressure. Angiotensin 2 also is going to go to the adrenal cortex and cause aldosterone to be released. Now, aldosterone is going to go to the distal convoluted tubule and cause sodium and water to be reabsorbed while causing potassium to be excreted. Angiotensin 2 is also going to go to blood vessels where it is going to cause vasoconstriction, which is going to increase CPR to increase blood pressure. ANP was a hormone that we talked about that comes from the left atrium. It's actually acting in the opposite direction of the renin, angiotensin, aldosterone system. When there's going to be a spike in pressure, it would be felt first in the left atrium. There would be stretch receptors in there that sense that, and that will cause them to release the hormone ANP. ANP will then go to the kidneys and cause the excretion of water and salt. It acts like an endogenous diuretic. Okay. Cross out the bottom of this slide, sodium, potassium, hydrogen. There's a relationship. It has to do with charges. So I explained this when I introduced aldosterone, why it was that aldosterone says if you're going to hold back sodium, if you're going to reabsorb sodium, you need to excrete potassium. It is to maintain the charges in blood. Okay. Of course, the kidneys have a role in maintaining pH. We said that urine is usually slightly acidic, like from 5 to 7, and that is because the kidneys are excreting hydrogen ions to maintain a pH. The pH is actually maintained within a very, very narrow range. I think other than blood osmolality, this is the smallest range we've seen all semester. Normal range for blood pH is 7.35 to 7.45. And you guys know why blood pH is maintained within that range. I wish somebody could tell me. The reason is because human proteins function optimally within that range. And outside of that range, they don't function optimally. If you go too far outside of that range, too high or too low, proteins denature. And if the proteins denature, then the cells die. Okay, so very narrow range for blood pH. This equation here, you've seen it, and seen it. This is the last time I will show it to you this semester. Bicarbonate is the most important buffer we have in blood. Okay. So a little bit more on acid acid-base balance here. There are two major classes of acids in the body. There's volatile and non-volatile. Volatile ones that can be converted to a gas like carbon dioxide in that buffering system. Oh, I showed you the equation again, sorry. Okay. Here it is. The non-volatile ones are the ones that cannot leave the blood as gases. So talking about like ketones. We've talked about ketoacidosis since the beginning. You guys know what lactic acid is, fatty acids, those okay. Anytime, regardless of the reason, pH falls below 7.35, it is called acidosis. Anytime pH goes above 7.45, it is called alkalosis. Okay, so then this can be caused, this meaning acidosis or alkalosis, and be caused by either the respiratory system or the other acids. So we saw respiratory acidosis and respiratory alkalosis, although we didn't call it that, when our breathing had an effect on carbon dioxide levels, which then had an effect on pH. So acidosis would be caused by hypoventilation. Hold your breath. Okay, right now, you're not breathing off the carbon dioxide at the rate that you're supposed to. So you're getting more carbon dioxide in the blood. You get more carbon dioxide in the blood, you get more acid in the blood, and pH goes down. I said that correctly. I'm just giving you a moment to think about that. Okay, with respiratory alkalosis, this we saw with hyperventilation. You started breathing really, really fast. Carbon dioxide levels in the blood went down and decreased the acid and made pH go up. Okay? We have seen metabolic acidosis, although again, we didn't call it that. Ketoacidosis is metabolic acidosis. Okay? Metabolic alkalosis, I think you had a patient in lab who had too much bicarbonate. It ended up being excreted into the urine, but if it was in the blood, it caused metabolic alkalosis. Okay? All right, we're going to finish up by taking a look at some kidney diseases. Acute renal failure, acute means short term, like something that's a bacterial infection, something that can be gotten rid of. Okay, essentially, this is going to affect the kidney's ability to do all their jobs. Okay, signs of this are going to be increased creatinine in the blood. Creatinine is a byproduct of using creatine phosphate. It's one of the three major waste products, the other two being uric acid and urea. Okay. This can also involve inflammation of the tubules. It can be caused by inflammation of the tubules, like from a bacterial infection, or ischemia. Remember, that was a lack of oxygen. Okay. With glomerular nephritis, glomeruli are inflamed. It can be caused by an autoimmune attack against the membranes of capillaries. That's going to cause proteins to leak into filtrate. And you guys know from lab, I'm not sure, I hope, if you have a decrease in plasma proteins, you're going to have a decrease in colloidal osmotic pressure, which is going to decrease absorption, which is going to increase the tissue fluid and result in edema. In renal insufficiency, the nephrons get destroyed by some disease. This is going to end up having the patient have something called uremia, which is where the urea levels in the blood are really high. Remember I told you that urea and uric acid, they are toxic, less toxic than their precursors. So they're still toxic, just that they're less toxic than their precursors before the liver converted them into something less toxic. Okay? These people clinically will also present with high hydrogen ion concentration in the blood, so you know their pH is being changed, and high potassium. This actually will cause a coma. This is going to be treated clinically by something called hemodialysis. Most of us just call dialysis. I'm going to tell you, dialysis, while it is life-saving, blows my mind how horrible it is. Essentially, since the kidneys aren't doing their job, what's going to happen is the blood is going to be taken out of the body, run through an artificial filter, trying to mimic doing what the kidneys do, remove the waste, and then it's going to be put back into the body. The reason I say it's horrible is because there are all these different filters out there, and none of them can mimic doing exactly what the kidneys do. As there are billions of dollars being spent out there by world-class researchers trying to figure out how the hell the kidneys do exactly what they do. So let me give you an example. Even with all of our technology, we cannot exactly mimic artificially what the kidneys do. Think about that. We've sent monkeys into space in spaceships. Look at the nanotechnology we have. We've been able to grow neurons on computer chips for over 15 years. We can't make a filter that mimics what the kidneys do. It's amazing. Some of these filters will wipe out plasma proteins. Oh my gosh, you know how important those are. So then there's a different filter that doesn't wipe out plasma proteins, that wipes out the ion balance. Oh my God, I knew somebody who did hemodialysis in the morning, and that night his mind was messed up because he had the filter messed up the ions. Your brain cells can't function. It's horrible, horrible. Again, it is enough to save somebody's life, especially if they're on a kidney donor list or something like that. But it's just horrible what these filters do to people. And I don't know if you guys remember, but in one of the last major elections, dialysis centers were hit hard because not giving the highest level of care to patients. It's just horrible. You wouldn't wish this on your worst enemy. Okay. It does allow urea, creatinine, and uric acid to be removed, and so use them. It saves lives. All right, guys, that's it. So listen, we are going to go ahead and start the exam for Monday night's lab. Wednesday night lab, you are excused. Monday night, we're going to go ahead and start it now because we're still in class, and it makes no sense to me to go break and then go take the test. It's 36 minutes, and we'll be done before the end of class. So I'm going to go open it up for you right now, and we're going to take it. Do you guys have any questions for me?
No. No, thank you, doctor.
Wait, Balan, I see you talking, but I can't hear you. Let me switch the
No,
speakers.
no, professor. No, thank you.
Try it again. What's that?
No, thank you, professor. No question. Thank you.
Okay. Just checking.
Yes.
Okay, I'm going to open it up now for Monday night. For Wednesday, have a wonderful day. I will see you guys on Wednesday. Be thinking about the chapters you would most like to go over on Wednesday.
Thank you, Professor.
You're very welcome. Have a great Wednesday.